Hi everyone and welcome into this new video. In this video I will show how to implement a Base64 encoder in C. This is going to be a continuation of a previous video in which I discussed about Base64 encoding. So what we're going to do today instead is to implement an encoder in C, a Base64 encoder. So at the end of the video we will have written this C file. So we have a bunch of libraries. We have the main functions to encode and decode in Base64. Here are the implementation of the functions that we will see. And here we have a simple main that wraps over those functions for user interaction. So at the end of the day, we have a makefile. We can do make all and it's going to compile. Notice that the library used are the math library and the readline library. So we can do Base64 and here we can say like hello world. And here is the Base64 encoded version of the string hello world. You can also write anything, please subscribe. And here we have the Base64 of that specific text. So if we want to cancel from the program, we can do Ctrl+C, we go out. And then if we want to decode, we can execute the program with the -d flag. So in the decode mode, we can write this time the Base64 encoded text, and we get back the decoded text. So here we decode the second thing, please subscribe. So that's the idea of the video. In the video, I will also take notes from the blog post I wrote in my blog, Base64 encoder in C. I will put a link in the description. So that's the idea. I hope it's gonna be fun, useful, and interesting. This is gonna be just C programming, so it's a bit more advanced. If you have some feedback, please leave it in the comments and subscribe to the channel. So I'm not gonna talk too much about Base64 because I've already done in a previous video. So if you have no idea what it is, what it's all about, just go watch the previous video. I'll put a link into the description. Now in this blog post, I describe the procedure for encoding and decoding. So this is the Base64 encode. So essentially the idea of the encode procedure is we start from raw bytes. These are gonna be ASCII bytes, so bytes taken from the ASCII alphabet essentially, and we're gonna transform them into Base64 data. So how does this procedure work? So let us now describe the encoding procedure. Before showing the actual code, we will describe how to manually encode the string hello world in Base64. This is what I always suggest when you have to implement a complex process. Just do it once by hand, understand the single instructions, the single transformations, and then you can write the code to automate all the process. So let's start with the string hello world. So to start off, remember that the ASCII encoding tells us that each character of the sequence is a byte, where each byte is a number between 0 and 255. And we can represent those numbers as follows. So here we have the text essentially, H, E, L, L, O, etc. Here we have the hexadecimal representation of the byte, and here you have the bit sequence that represents the byte. So these are going to be 8 bits, where each bit is a 0 or a 1. This can also be written in decimal notation. Here I'm not putting the decimal notation because we don't really care about that. When it comes to Base64 encoding, we are interested in the binary representation because that's how we're going to process the numbers. Now, the main idea behind encoding in Base64 is to consider the sequence of characters as a stream of bytes. So we just consider this stream of bytes, these sequences of bits, each of which is made up of 8 bits. So each byte is just 8 bits. Perfect. Now, the idea is that we want to split this sequence into 6-bit blocks instead of the original 8-bit blocks. What does it mean? It means that the original byte was 8 bits, but now we want to work with 6 bits. So we want to take 6 bits here. We do not consider the remaining 2, so that's the idea. So we want to split up the sequence in 6 bits instead of the original 8-bit blocks. So this means essentially that every 3 bytes of the original output, so here we have 3 bytes, then we have 3 bytes, then we have 3 bytes, then we have 3 bytes. So every 3 bytes, we are splitting these into 4 blocks of 6-bit each. So they are 4 blocks of 6 bits. If you do the math, essentially, you can write 3 times 8 is 24, which is also 4 times 6. So instead of having 3 blocks of 8 bits each, we have 4 blocks of 6 bits each. So for example, consider the first 3 bytes of hello world, which is the byte for H, E, and L. So let's split them up in 4 blocks of 6 bits each. So notice, how is this splitting up done? Well, I can take this. So let's do that in Emacs to make sure that we understand. So what do we do here? We do text mode. So what do? We take 6 bits. So these are 6 bits, and then this is our first 6 bits. Then we sort of like concatenate all together. First we concatenate all together. Then we take 6 bits, so that's 2, 4, 6. Then another 6, then another 6, and then we have these 4 blocks, each one is of 6 bits. So this is essentially what we obtain. 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, etc. So that's the idea. Now the split is done by simply going from left to right and taking each time blocks of 6 bits. Sometimes you have to append bits taken from different bytes, but we always do it from left to right. So like the idea is that, for example, in the first case, since we are taking 6 bits from this byte, we are just left with the 2 remaining bits here, which we have to append to the 4 bits here. So this is how the split is done. So and now, once we have all the blocks of 6 bits, we extract from each of those blocks a character by taking the numerical value, that is the decimal value of each block, and by using the Base64 encoding table. So what does it mean? It means that, remember, Base64 is an encoding, and an encoding defines a mapping between numbers and characters. So here, look at this. Number 0 is mapped to A. Number 1 is mapped to B. Number 29 is mapped to lowercase d. Number 42 is mapped to lowercase q. So we have this mapping going on. And now that we have splitted the stuff into like blocks of 6 bits, we can take the decimal value here, like for example 18, and by using the previous table, we can assign to this value a specific character. So for example, S or G or V or S. So like in this case, it's capital S, lowercase s. So we have this, and essentially these are the first 4 characters in our Base64 encoding. So these are the first 4 characters, and we can decode the rest. So that's the idea essentially. To decode the rest, what do? We consider all the remaining sequences of 8-bit blocks. For each 3 blocks of 8-bit each, we split them into 4 blocks of 6 bits. So we have 3 sequences remaining. This gives us 3 sequences of 4 blocks where each block is 6-bit. And then we just use this transformation to obtain the remainder. And at the end of the day, we obtain the encoding of the hello world. So this is the idea essentially to manually encoding Base64. Now, of course, we don't want to do it manually. We want to do it using a C program. So that's where essentially the magic happens. That's where we can write our actual program. So we're gonna write, so let's say this old, I'm gonna rename it into, let's say, old base64.c. I'm gonna create a new base64.c. So what do I do in this? Well, first things first, we're gonna include a bunch of libraries. So for example, stdio, we include stdlib, we include assert, we include math, we include stdbool for the boolean type, and we include readline, readline.h, and readline history.h for the readline capabilities. Then we define the function signatures. So we're going to have 2 main functions, Base64 encode and Base64 decode. Now the types of this function is so defined. So we have 3 arguments. We have a const chart pointer input, which is the input. Then we have the unsigned long input length, and then we have the output. Notice that while the input is const, the output is not, because we have to write to the output essentially. So that's the idea. And here we have a pointer to a constant character. So here constant is the memory that is pointed by the pointer. And here we have an unsigned long of the length, which is the length. And the decode essentially is the same. It's just that the way we're going to interpret it is that before the input are ASCII bytes, in the decode the input is going to be Base64 bytes. So that's the idea. Then we have the core implementation of this function. Implementation. So we take this function and we just write the code itself. So to do and then to do. So before actually implementing this, what we need to do is we need to define the mapping between letters and numbers. So the thing in the blog post here that I show, essentially, this mapping And how do we implement this mapping? Well, the idea is to use a string like this. Now, why does a string like this works? Because this string actually contains two types of information. One is the value, and the second is the index of the value. That is, the index of the value is the number, and the value is the value that is mapped to that index in a way. So, if, for example, the mapping here is 0 is mapped to A, then we can put in the first position A so that its index is going to be 0. Then it's going to be 1, 2, 3, 4, and so on and so forth. So when we want to access, when we want to convert from a number to the character in base64, we just do base64 the array, and then here we put the index. We put the index, and we're going to get the correct number with respect to the base64 encoding. So this is pretty straightforward. We are using the C like string construct. So that's the idea. So we can work to implement the encode procedure. So now we can actually move on and implement this function. So how we're gonna do it? Well, first of all, we're gonna have two indexes. So we're gonna do input index and output index, and they're both gonna have value of 0. So 0, 0 for both of them. Then we do a while loop, and the condition for the while loop is while input index is less than input length. So input index is going to be our index that will cover all the input, all the bytes of the input. So we say until we have something yet to see, until the input index is strictly less than input length, we do the computation. At the end of the loop, we do output, and then we say output index. We write the 0 string, the null string, to say this is the null character, this is the null character, and it says the string stops here. This is because in C, string buffers, which are buffers of character essentially, have, in order for them to be processed correctly by the various functions offered by the standard library of C, it is assumed that here you have a bunch of character on the various string, on the buffer, and then at the end, the last character of the buffer has to be the 0 byte, the byte with the value 0. So this is how we write it. This is the essentially the to say, look, the string has ended. So that's the idea, and then we just return. We don't need to return a value. Why? Because we are writing stuff on the memory pointed by the output pointer. So that's the idea. Now at this point, we can actually process the string, and as we said, in each iteration, we're going to do in each iteration, we process 24 bits of the input. That is, we process 3 bytes. So we are processing just 3 bytes of the input. So that is, we have to process the first 6 bytes, the first 6 bits, the second, the third, and the fourth. Third and fourth. So how do we process those bits? Well, the idea is to get them out. So how do we get them out? Well, first of all, we can access the value by doing input, and then we do input index, and this is the value of the current byte that we are analyzing. Now, what's the idea here, however, is that, remember that, let's say we start with, what was the initial sequence of bytes here in the example? So we go down here. Let's say we start with this byte, right? So we start with this. So if we just access the byte itself, we have this value. However, we are interested only in the first 6 bits from left to right. So how do we extract only those first bits? And the idea here is to use essentially like specific operators in the C language, which are called bit operators, that allows us to interact with the specific bit mask, with the specific sequence of bits. So what do? We take the bit value, we do an end mask with this specific value, 0xfc, and then we shift everything by 2 to the right. Now, this specific value is going to be the value of only the first 6 bits. Now, why is that the case? Well, to extract it, we do the bit mask, which is this operator, with this specific sequence of bits. Now, this one, if we have to spell it out in bits, because this is written in hexadecimal, right? If we have to spell it out in bits, this is going to be 1, 1, 1, 1. So these 4 ones are for the F, and for the C instead we have 1, 1, 0, 0. So this is the bit representation of this 0xfc. So when we do this bit mask, what we obtain essentially is we just obtain the first 6 bits and not the last 2. The last 2 we ignore. So we're gonna have like 0, 1 0 0 1 0, and then here 0 0. So this is the number essentially we obtain, and then we do a shift on the right by 2. So this number is gonna become, we shift the following. So we do 0 0, we introduce 2 0 on the left, and we remove the last 2 characters on the right. And so this is our new number. And essentially this number is constructed in a way that the last 2 bits, the one on the left, are always 0, and on the right we have the first 6 bits that were present in the original byte. So this can be a bit confusing if you don't know bit operation, but the general idea is pretty simple once you know about those operations. So once we have this number, we have to use the Base64 here array. And this is how we actually access the value. And this value, we're going to write into the output. So we're going to write into the output. And after we write it, we increase the output index. So this is a little bit of C syntax where we say, look, we access the output using the output index value. And after we use that value, we increment it by 1. So we go to the next index value. Now, what do we write in the output index? We write the character that was present in this array by using the offset, by using as an index value, the one obtained by processing the first 6 bits. So that is how we process the first 6 bits. So we can move on to processing the second 6 bits essentially. Now here the idea is a bit more complicated. Why? Because consider this. We have, so if we just go back to this, we have the first, so let's say this one, okay, it's good. And then the second one, the second byte. So we have the first byte and the second byte. Now this one have been processed, so we don't care about them, we can just eliminate them. Now for the next sequence of 6 bits, we have to take the last 2 from the previous byte, from the current byte actually, and then 4 more from the next byte. So this is interesting. And so we have to combine those 2 to obtain essentially the sequence 0 0 0 with 2 0 at the left here. So this is the final byte that we want essentially. So how do we do that in code? So the idea is that we are going to do a similar thing. However, we start with the current byte. We do this time an end mask with 0x3, which is the final 1 1. So it's like 0 0 0 0 0 0 1 1. So this is the bit mask. We shift this to 4. We shift it by the left with 4. So we do this shift. And all of this is going to be OR together with another value, which is going to be the next byte. So this is the next byte. And how do we process the next byte? We just want the leftmost 4 bits from the left byte, from the next byte, sorry. So we do 0xF0. We do an end mask like this. And then this one we shifted to the right by 4. So we shifted to the right by 4. And essentially we have our number. So this is our number. What do we do with this number? We use it to access the Base64 array, and then we just write it into the output. So this is how we do process the second bits. Now, once again, let's try to review it. This instruction is to obtain the first 6 bits. This one is to obtain the second group of 6 bits. However, this time it's a bit more complex because we have to take the last 2 from the first byte and the first 4 from the second byte. So to obtain the last 2, we do this. We take the last 2 bytes and then we shift them by 4 position. So we have first 2 bytes and then 0 0 0 0, like 4 zeros. And then we fill up those values with the 4 from the next byte. So we extract the 4 from the next byte, we shift them to the right by 4, and then we combine together with OR. Now, notice however something that happened. Here, I access the next byte. So the question is, wait, does this byte even exist? Because by the construction of the loop, I know that the input index is always less than the input length. So I am sure that this byte does exist and is fine. However, I'm not sure with the opposite. I'm not sure with respect to the next one. Does the next byte exist? Not sure. So I have to sort of like handle the case to do handle padding case number 1. So I have to handle the case where I'm trying to encode something in Base64 that has only one single byte. So I have to handle this and we're going to do it at the end. So before doing that, let's do processing the third byte. So to process the third byte, I'm going to use a similar like idea. However, it's just going to change. What's going to change? It's going to change how I put together the bytes. So from from the +1, so from the next one, what I want is, I want the final 4, so I'm gonna be 0x, 0f, so this is gonna be the final 4, and I'm gonna push them 2 position to the left. And so with this first instruction, I am taking the second byte, so I'm taking the second byte, and I'm extracting the final 4 bits. So this is 4 bits. Of course, I still need 2 more bits to have a 6-bit block. So where I'm gonna take them? I'm gonna take them from the next byte. So if this is our original, orig, this is orig +1, and this is orig +2. It's the +2 byte. And from here, I just need the top 2 bits. So what do? Here I put input index +2. Here I do an nmask with 0xC0, so 0x lowercase C0. And to make sure that they combine with this other one, that they have the right place, I have to shift them to the right by 6 actually. So I have to shift them to the right by 6 because they are the left 2 bits. So I have to put them as the lower 2 bits of the number. So this is the third number, and then, once again, what happens if the +2 bytes does not exist? So I have to handle another padding case. So I have to handle padding case 2. And finally, process things, and finally I have to process the fourth one. So the fourth one is simpler because, well, I can take the first one that I started with. At this point, the last 6 bits are all taken from this input index +2 position. So I say input index +2 position, the mask here is 0, 3f, and I don't have to do any shift whatsoever, because this mask 0, 3f essentially is 1, 1, 1, 1 to the left, and to the right is 0, 0, 1, 1. So I shift by this, I obtain the last 6 bits of the byte. And once I process even this one, what do I have to do? I have to do input index plus equals 3. So I jump to the next group of 3 bytes each. So this is almost done actually. We just need to handle the padding cases. So how do we do this? Well, the idea is we check, look, if input index +1 is equal to the input length, so we are done with, we are over. What we do is remaining bits that needs to be processed are the rightmost 2 bit of one of the last byte of input. And we also need to add 2 bytes of padding. So here we have 3 bytes, of course, they need to be written, but this time the bytes are gonna be the rightmost 2 bit on the last byte of the last byte, and also the padding bytes. So for the padding bytes it's simple because the padding byte is unequal in Base64. So we have 2 equals, and then here the value, it's like we take this, and then we put the mask is 0x03, and then we shift to the left by 4. We shift to the left by 4, and we have our padding. Now, why do we do this? Because remember, after we are here, what we did essentially is we have 8 bits here, right? But we already taken the 6 bit. So the only one that we need are the 2 here. So the idea is that we take the 2 ones and we do this shift because the number we consider is going to be the one where we have the 2 bits here. Let's say that they are 0, 1. So it's 0, 1 and then 4 zeros. This is the number we use to compute the second character in Base64, and then the remaining is just padding. It's just this kind of padding. And indeed, this mask just gives us the 0, 0, 0, 0, 0, 0, 1, 1. So we have 4, actually we have like 4 zeros, this is 4, then 2 0 and 2 1s. So this is the bit mask associated to the number 0x03. So this is the first padding case, the padding case number 1. Then we have the padding case number 2. How is we're gonna resolve it in a very similar way. So this time we're gonna do like this. So it's handle padding case number 2. This time we don't have to put 2 equal characters, we just have to put 1 padding character. And here we put a Base64 input +1, and from this +1 we need to extract the last 4 bits. So we can do 0f, and then we shift to the left by 2, essentially. So are the rightmost 4 bits of the last byte of input, and we also need to add a single byte of padding. So that in general, with these extra padding bytes, now the code is covered. And notice, so we know that we can access this value, so it's safe. Then we check for the padding case to make sure, wait a second, is the next byte valid? If it's not, we handle that case and we can return. Here you can do break, so we can break from the loop. Then we process the second group of 6 bits, then the third and the fourth. If there is no third byte, we stop once again, we do a break, otherwise we just continue, we just keep going. And this is our encoding procedure. Now, to make sure that we wrote it properly, because it can be confusing with all this bit mask, with all this shift, we could have made some errors. So what's the idea? Let's write a simple wrapper to the main. So we say, these are the function signatures, then we divide, this is the core implementation, and this is the main function that allows us to call the code, essentially. So we say int main, int argc, so here down you can see the code, char argv. So we say bool the code mode, for now we put it as false, and this is going to be triggered with the -d flag, but we don't care about that now. If the arguments are greater than 2, we already know that something is not good, because we have at most like 3 arguments. Say usage, and then here we put the name of the program, and we put in square brackets the -d flag, and here we put the name of the program, and then we say return 1. Otherwise, we parse the arguments, but of course this is like an extremely basic and elementary parsing routine, and we only do that when we have exactly 2 arguments. So we do the code mode, we do a memcompare with what? With argv1, so the second argument, -d, the number of characters is 2, and then we say if this is equal to 0, then we are in the code mode, because we are saying, look, if the second argument is equal to /d, then memcompare will return 0, so we're gonna compare it to 0, so this is gonna be true. This is gonna be like true in C. If we are not in the code mode, then essentially we have an error, because if we have a flag, the only flag we can use is the decode mode flag, so scdr. So we have an error, options allowed are, and then here we put the only options allowed, which is -d. So essentially this is it for now. So let's just say return 0 here, and let's write, we have this simple makefile. I'm not gonna write it, it's very simple. We just have some C flags, some libraries, which are the -lm and -l readline. We still have to use the readline and the lm, but we're gonna need them. And we have a target all that depends on the file base64c, and we just simply compile it. This is basic syntax. So it says express identifier. So what's the problem here? Int, wait, let's see, maybe it's the version of the C standard that does not allow for this. But if I do this, no, so it doesn't work. So let's just do it in a 2 way. So we do this, and then we do this. Okay, so we have 2 instructions for assigning the values. Perfect. This is a basic, so like we compile it, right? We can also remove it with make clean, which just removes the file. So we compile it and we execute it. Of course, nothing's gonna happen, but if we put a wrong flag, it says, look, options allowed are -d. And if you put more than 2 arguments, it says, look, the usage is call me with at most the -d flag. So this basic logic is fine. So at this point, we enter into the main loop here. So what do we do in this main loop? We do a while until what? Until essentially we have the end of stream, f with standard input. So if we reach the end of stream, we just quit, otherwise we keep going. So we say input equal readline with the empty string, or maybe you can say base64 like this. And we have, if we have no input, then we break. Here we say break, so we go to the next, I guess we can also say, we can go to continue, we go to the next iteration. So, okay, and then we say unsigned long input length, we do s3ln of input, so we just check the input, and we also define the output to be null for now, because we're gonna like encode it in the future. So let's just print our string here. Let's just print the input here. And we are using the readline function. Now, when you use standard C library function, you always have to understand who manages the memory, what is the memory management scheme to follow. In this case, you can do a simple main read line, and it says essentially that the caller, the line return is allocated with malloc. The caller must free it when finished. So since here allocation happens with malloc, it is extremely important to free it ourselves. So after we print it, we're gonna do free of input. Otherwise, we have memory corruption error. This is why programming in C can be dangerous when you don't handle memory correctly. Anytime you have a piece of memory, you have to understand who allocated it, when did the allocation happen, and when the deallocation has to happen, when the freeing has to happen. So this is it. You can just compile it very quickly. I'm gonna see unused variable. We don't care about that. We can just do it like this. Notice that I get this prompt, and when I write stuff, I get stuff back here, so that's good. And I can just quit it by doing Ctrl C. I do Ctrl C and I'm out. So the stuff that we need right now is, if I am in the code mode, if the code mode, I'm gonna do nothing essentially. I'm just gonna break because I don't have it supported. Otherwise, I am essentially encoding. So this is the code, this is encode. This is the code and this is encode. So encoding, we're able to encode. So how do we encode? Well, the idea is that we have to allocate the buffer. So we do output equal malloc of a certain size, output length. But of course, this output length is not defined yet, output length. How do we define this output? So here I can just say like this. How do we define this output? Well, we can just compute it by considering the fact that, let's do this computation. So let's say that the input has like 30 bytes. Now the output, for every 3 bytes of input, the output will have 4 bytes. Because remember, for every 3 characters, essentially, we're gonna have 4 characters. So what's the size here? The size is, it's like we divide by 3 and then we multiply by 4. So it's like the size of the input size times 4/3. So this is the new output. And then we have to add a +1 to consider the empty string, the final terminating null character, to say that the string is over. So we have to add this. So what do we do here? Pretty simple. We say, okay, output length, we say ceil of input length divided by 3.0, and then we multiply this by 4, and then we do a +1. So that's the idea essentially. And then here we do Base64 encode. We do input length, and output. So we put the input with the length. We're not gonna write into the input, we're just gonna write into the output that we fill up with essentially this code. And once we do that, we can actually print out the output. So we do printf, it's a string of the output. So let's compile it right now. We do make, we do Base64, please subscribe. We get this back. Let's see if by doing a echo -n, please subscribe to the official Base64 command, what do we get? We get the same string. So notice here what I did. Top, I use my program, my routine that we just wrote together. In the bottom here, I use the official Base64 binary. So here we can see also the path, and I can also put the entire path instead of just the name of the binary. It's the same. And notice here, it's the same string. So we have a matching, this is good. Of course, this is not like how you should test a program. You should have way more robust testing, but for this video, this is gonna be good enough, otherwise it's gonna be way too long. So be careful about the computation of this length, that the number match up. I think that they match up. If you find any bugs, just write in the comment. So the last thing that we actually need is the decode procedure, because now we're able to go from a normal ASCII string to the Base64 version by processing them in chunks of 6 bits each. Now we sort of have to do the reverse. Starting from the Base64 string, we have to go back to the original ASCII string. So when it comes to the decoding procedure, it's going to be similar but in the reverse order. So we're going to have our indexes in the input and output as before. But this time we're also going to have the 4 bytes. So we're going to have first byte. Actually, just call it first, second. Actually, let's see if it compiles with second, third, and fourth. So these values have to be initialized. So let's try to see if it compiles. Okay, it compiles, it just says unused, perfect. So we say, so here the first thing we do is we make sure that the input is properly formed. Why? Because we can only decode something that was previously encoded in Base64. So the first thing is check if the input length is an even multiple of 4, because as we said, since for each byte of the original input we get 4 bytes of Base64 output, it means that the Base64 output is always a multiple of 4 with respect to the length, because we also have the padding to make sure that this is the case. So what do we do in this case? The idea essentially is we do if we take the input length, we do the bit mask with the value 3, so 0x03. If this is different from 0, 0, so if this is not 0, 0, so if not this, then we have an error. Why? Because all multiples, all even multiples of 4 in their binary representation, they must end with 0, 0. So they must end with 0, 0. So by doing this, we extract the last 2 bits, and if those are different, if they are different from 0, 0, then we have an error. So we say essentially fprintf, we say error, invalid Base64 input length not even multiple of 4. So this is essentially the idea, and we can just return 1. So this is the first check. Then we do the usual loop where we go through all throughout the input. So we say input index less than input length, and here we decode the everything, and then here output index equal to the 0 string, to the 0 byte, and we return 0. So the same as before. So in this case here, we have to do essentially reconstruct first byte, reconstruct second, third, and fourth, second byte, third byte, and fourth byte here. So here essentially we have to extract 4 bytes of the input. Those are Base64 bytes. So we have to put this, we can actually put them inside a loop. We can actually put them inside a loop. And essentially we're going to say first, and we're going to use a special table, which we called unBase64. So we say unBase64 of what? We're going to do int input, and then we're going to do input index plus 1. And then we're going to do second. Actually, the first is going to be just input index. Third and fourth. Third and fourth. Plus 1, plus 2, and plus 3. This means that this time we iterate through the input by 4. So we do input index plus equal 4. Now here we have to reconstruct the first byte, second, and third. But before doing that, we actually have to make sure that those bytes are valid. Now, how does this unBase64 table work? The idea is that it's going to be defined as follows. Here I'm just going to copy it and discuss it later. So it's essentially this table. So this table essentially implements the mapping from the 8-bit to the 6-bit Base64 value. Now, why do we need this table? Because in terms of computer memory, even after we extracted our 6-bit, so even after we extracted this 6-bit, actually this 6-bit is represented by the computer always as an ASCII byte. So it is always represented with 2-0 on top, like here. And so we always deal with sort of like single bytes. So this table allows us to go back from the byte to the 6-bit value. And it is defined as follows, essentially. So in the input of this unBase64, I put the 8-bit value that is present in the character, and back I get the original 6-bit value. So I do this with essentially the 4 bytes here. Now, before doing this, actually, I can check if the bytes are valid. So I can say I do a loop for I equal 0 until I is 4, I plus plus. Then I say, look, if input of input index plus I is greater than 131, or when I unbase it, when I unbase the value, so here I can say int value, say this value. If the value is greater than 161, or when I unbase the value, I get a -1, so it is not mapped, then I have an error. Then I have an error that I put into the standard error buffer, sort of. So I say error invalid Base64 character cannot decode, and here I put the single character that I'm not able to understand. So here is the value. So that's the idea, and then I return -1 within this if. So that's the idea. Here I put semicolon, and here I put this single for. So this single for is make sure that the next 4 bytes of input are properly encoded base64 data. So we do this check, then we extract the the 4 values, the 4 6 bits values, and then we reconstruct the original byte. Now to reconstruct the byte, we have to take bits from the various elements. So how do we do this? We say output of output index, and then we say, look, this is equal to first, we shift this to the left by 2, and then we say second, we extract only the rightmost 2 bytes, the rightmost 2 bytes, yes, and then we shift them by 4. So this is gonna give us back the original 8-byte value. So this is the first byte reconstructed. So in terms of the block post, for example, let's just consider this. So we have the 2 6. So we have this is the first 6, and then this is the second 6, right? So we want to take this. We want to sort of shift it to the left by 2 to add this 2. Then we want to take this. We want to only consider the rightmost 2 bits. So we want only to consider these 2, and then we want to OR them together to obtain essentially the final byte. So this is a lot of operation with single bits, but it's sort of a good exercise to operate with this kind of C constructs. So we do this, then we reconstruct the second byte. So if input of input index plus 2. Now if this is different than equal, essentially we do this. Otherwise, so the second byte is only to be reconstructed if we do not have padding, because if we have padding, then we reconstruct only the first byte. So how do we reconstruct the second byte? It's similar. However, here we have to say second, and we have to extract, we have to unmask with the last 4 bits, and then we have to shift by 4, and then we do an OR with the third, where we extract the middle 4 bits, and then we have to shift them by 2, and this is it essentially. So we reconstruct the third byte, and there's no fourth byte actually, so there's no fourth byte to reconstruct because there are only 3 bytes. So we do a similar thing, but this time we have to check if +3 is not padding, because we only reconstruct the third byte if we do not have padding. And in this case it's much simpler, because we have we have to do third mask with 0x3 03, we shift by 6, and then we OR it together with the fourth byte, and essentially this is it. So all these operations are to reconstruct the bytes. Then we have this. To test this code, we go back to the main essentially, and the idea is we go to the decode mode. Here we check the unsigned long padding length. So we check the padding length. How do we check this? We say, we do this computation. If the input length is greater than 1 and the last byte of input, so input length -1, is equal to the equal sign, so this is one thing. In this case, then, so we check is the last byte of padding. Then here in this case we have to check, so let's see this one. Okay, that's good. And actually let's put it like this. Let's put it like this. Then we check if also we have 2 bytes of padding. If we have 2 bytes of padding, we return 2, otherwise we return 1, and otherwise we return 0. So this is the idea. So this just checks essentially the what we implemented here was, we say, look, is the last character in the string just 1 equal? Is the second to last just 1 equal? In this case we have 2 bytes of padding. If it's just 1, we have 1 byte of padding. If it's not even 1, we have 0 byte of padding. So that's the idea. Once we have that, we can compute the output length. So output length is going to be equal to 3 times the ceiling of input length divided by 4.0. Then we have minus the padding, because we don't care the padding, and then +1 for the last byte of the string, which is going to be the null byte. Then we can just malloc the output length, and we can call Base64 decode with input, output, and input length. So here is input length and output. So we can do the operation, and then we just print out the output. So let's see if this works. So there are a bunch of errors here. So I can actually compile within Emacs, make all to have it suggest the errors. So here I have to put the stream, of course. Here I have to put -1. Actually, let's say, okay, no, I don't have to return anything because it's a void operation, it's a void function. So here I have to put semicolon. Here I have to put nothing, just return. Here I have to put padding length. Okay, we're good. We compile everything. We're gonna say please subscribe with a question mark, with the exclamation point. Then let's try to decode it. It says the output, the length is not an even multiple of 4. So actually here there was a mistake because I put the exclamation mark here and actually should not be here. So the idea is when I take this input length and I do the bit mask with this value, I should have the last 2 bits of the number. Now, if the last 2 bits are 0, then I do not enter into this if, and it's good. If the last 2 bits are different than 0, then I don't have a multiple of 4. So I type it wrong. It should have been without the question mark, the exclamation mark. So let's say, please subscribe, and then I decode it. Let's try, and I get nothing back. Let's see why in this case. Because I have a break here, of course. Break here, gonna put it back here. I get nothing back still. Okay, here there's another error. Here, once I write with the output index, I have to increment by 1. Increment. Anytime I write to it. So that's it. So let's do make, let's do -d. And here I have my please subscribe string. So I can encode something, hello world. I can decode something like this. And so this is our Base64, this is the new one that we wrote. So it's comprised of 2 functions, encode and decode, and it uses these helpers, this data structure, to help going from the traditional ASCII byte to the Base64 byte, and from the Base64 byte to the traditional ASCII byte. Technically, this unbase is used to get back to the 6-bit value, to the original 6-bit value that is lost when we have to represent the Base64 character using ASCII. So this is helpful to have. And these are the 2 routines that we implemented, encode and decode. So I hope it was interesting. If it was so, please leave some comments, and to the next video.